I'm hoping, oh, there's Alex. I'm hoping that we will get through this quick. Oh, there he is.
Pardon this interruption for morning update. Good morning, everyone at AHS. For your safety and the safety of others, please note that health pre-screening is required for every person before you enter our campus. Hazel ISD and Hazel High School, we do follow all CDC requirements as well as all the Tarrant County Health public guidelines in regard to COVID-19. Again, we're glad you're here this morning. School safety is a top priority for our school. So we'll just remind you, faculty and students, any concerns, please don't hesitate to contact one of our officers in the hallway, one of our administrators. We'll be glad to assist you. We do ask that everyone on our campus, please be sure you're wearing a mask that covers your mouth and your nose. As well as students, please be sure you have a district ID around your neck. We appreciate that. Just to let you know that if you do not have an ID, you can get the QR code in the library, and the librarians will be calling you in to get your ID. And we need to be sure that we wear our ID. We'll be talking more about that next week as well. We're glad you're here this morning. We hope all of you have a great day here at AHS.
Okay, so let's see. Well, how many people am I missing online? All right, I'm going to start with what things people are missing. I'm going to go off of the, no, I have to do it through Canvas. Can't do it off my paper. Well, and that's, I just checked it this morning. If you did not do the one from Tuesday, it's locked and I'm not opening it unless you're one that has been sick and has been out. Obviously that's that. But if you just decided not to do it, then no. So what is open? Okay, the ones from, let's see, we didn't have school Monday. So Wednesday, if you're missing something from Wednesday, it's going to close at midnight tonight. Same thing, it's closed. So I'm missing both the opener and the assignment Wednesday from Otis. I'm missing both things Otis from yesterday. Caitlin, who I don't think is online yet, but I'm missing the assignments from yesterday and the day before. That person's not in my class anymore. Erica, the assignment from yesterday, but that's open until Monday at midnight. The one from yesterday, so you're doing good. And then Colton, the assignment from Wednesday, and then both things from yesterday. I think I just got everybody. It looks like most of you are doing pretty good keeping up with stuff. Let me go into what we're doing today. All right. I'm sure you're going to know the answer to part of this opener, but I don't know if you're going to know the answer to the other part of the opener. Depends on if you're up to date with this type of current event. So the easier one that you probably know, how do we look at the seafloor without actually physically going there? Okay, it's really, it's basically a combination of two. So you can use sonar. Okay, and if you just basically shoot sound and then it calculates with the echo how, just the timing of it, how deep was that object that it's pinging off of. Sonar and radar are essentially the same thing. One uses light, and so that won't work super deep. The other one uses sound, but it's the same concept. You fire something at an object, not like a gun, not like that kind of fire. Fire something at an object and you time that echo, whether it be an audible echo or visual echo. We do this with satellites in space now. Obviously, we didn't have that for a long period of time, but now that's what we use. But yeah, ships still do that. They ping, they use sonar. Right, Cameron. Now the part that you probably don't know, Victor Vescovo has gone down to the Challenger Deep twice. He's the only person to have gone twice. He holds the record for the deepest dive within a submersible. What do you think he found at the very, very, very bottom? Besides a bunch of seafloor silt. Obviously, that was everywhere. What do you think he found down there? What? Trash. Yes. Plastic. candy wrappers, plastic bags. Now, you did find some organisms too. You did find life. You know what kind of life is living down there? You are so close. It wasn't plankton. It was a type of prawn. Okay, so a type of shrimp crustacean, but not as small as plankton. And it starts with an A. It's like an amphithod or something like that. I'm not a biology teacher. That's a scientific name. But he also found fish. They were called snailfish, and they were pink, and they didn't have eyes. Well, they had sockets, but they didn't actually have eyeballs. Really weird.
So it's like the fish that light up like
No, it's not an anglerfish with the big teeth and
I've seen some like on documentaries how like they're like see-through almost.
Yes, translucent. There's the weirdest looking fish, not that I've ever seen it personally in life, but images in documentaries. The thing has like have you ever seen the really corny movie Mars Attacks? The aliens that are, okay, man, dang it.
They
Okay.
took like the lights of the flashing back.
No, they have like the top of their head is completely see-through. And you can see like, oh, I'd have to show you a picture. It's so hard to describe. There's the weirdest looking organisms. The deeper you go, the stranger they get. But there is a lot of bioluminescence, the fish that create their own light. Deep in the ocean, some of them use it as a self-defense mechanism. Some fish, when they flash, it attracts squid.
Is it that?
And then the squid come and attack what's trying to attack the fish. Yes, that. Weird looking, isn't it?
Mm-hmm.
So very, very, very strange things that we find within our ocean. We actually know more about space than we do the bottom of our own seas. So we're going to be mapping the Earth's surface. We're not going to get into reading topographic maps until Monday. I think I changed it. If it says tomorrow on here for topography, I mean Monday. Obviously, we're not coming here tomorrow. But the topography, okay, is going to be whatever that map is of. It would be the United States, Hawaii, Canada, I don't know. It's going to include the elevation of whatever that map is. And it has lines that connect areas that are equal elevation. We call those contour lines. Similar to when we did air pressure, you had those isobars that anywhere that line that had a number on it touched, it was that pressure. It's the exact same concept, but now we're doing elevation. Relief, which has to do with the lowest part of an object and the highest part of the object. And then landforms, things like mountains, streams. Sometimes they include bridges and railroads, streets, buildings. Obviously, not all areas actually are inhabited, but if they are, they include those kinds of things. Elevation is how high your feet would be on the ground above sea level. Altitude was different. Altitude is how high up in the air you are if you're in a plane or a hang glider. Parachute. You're in the air, you're flying in some way, shape, or form. Like I said, relief is the difference between your lowest point of whatever landform you're dealing with and its highest point. I didn't do a lot of things in blue just because everything would be blue. And I guess you can abbreviate if you want to. Let me double check real quick online and see if anybody else. Like I said, if you are coming on and you missed my sort of roll call about this is what you're missing. If you did not do, oh, there's Kaden. Did I get Kaden before? No. If you did not do the one from Tuesday, it's locked. It's gone. If you did not do the one from Wednesday, that locks at 11:59 tonight. And if you did not do the one from yesterday, you have through the weekends. The only real exception of me taking things is I have one student that had a family member pass away over the break. She's gone. She has obviously extenuating circumstances. I've got a kid that's on vacation, hasn't been here. So yes, there are some reasons why I would still take things, but I'm gonna have to go back and open them up specifically for those students when they come back. Oh, there was one more. Landforms. They are very specific features that are in that particular mapped zone. You have a mountain range. You have a plateau. You have a delta. Is there an island? Are there deep depressions? Is there a crater? Is it like Arizona, where there's a huge crater in the middle of Arizona that came from an asteroid strike? You can actually go down into it. It's a little town at the very, very bottom. So all of those, and we are going to get into landforms today. I'm not going to go into how the water cycle yet. I'm not going to get into how rivers work. We're not getting to any of that until probably next 6 weeks. Because plate tectonics will take through next week. We'll have a test in a week over what we're doing. We still have to do a little bit of plate tectonics, talking about what happened to Pangea when it broke up, because that leads into the mass extinctions. And we have to do the history of life, which is essentially evolution. It's not going to be like what you learned in biology, though. We can't go into depth about like how horses originally were the size of dogs and they had toes, and then eventually over time they evolved into what they look like now. We don't have time to get into all of that. But yes, horses used to have toes. They're called eohippus. And they were like, seriously, they were like this big. They're really bitty little things. Right. Types of landforms. I am hoping that we will get through this rather quickly. So if you needed to get your stuff caught up, you have time to get your stuff caught up. And like I said, I'm not going to go into extreme detail with any of these. We're identifying the major landforms so that when we do topography and maps, you know what I'm talking about. I'm sure y'all know what a plain is. It is not 100% flat, okay, but if there are hills, they're very, very gently sloping hills. It's not a mountain range. Compared to where Austin is, if you've ever been to the hill country in Austin, they would consider this area flat. And so it's just an image. Yeah, you've got a little bit of structure over here, but in general, it's a nice gentle slope. If they had a topographic map, if it showed a change in elevation, those lines should be rather far apart. Because the further apart a contour line is, the more land had to be covered in order to increase that elevation. The closer those lines are together, the less land was actually covered in order to go up that same increase in elevation, and so you have a steeper slope. That's what those maps, have you ever seen one of those? That's what those rings mean. We should know what mountains are by now, even though there aren't any around us. You have a high relief. That means from the bottom of the mountain to the top of the mountain, you have a large increase in elevation. So those contour lines would actually be very close together. The higher the mountain, the closer together those contour lines should be. Now, mountains come from converging continental plates. That is not new. We've talked about this. You have two granitic continental plates. They come together. They will not subduct. They have essentially, not 100%, but essentially the same density. So one doesn't go under the other. They have no choice, if they're coming together, but to buckle upwards. Now, you will find marine fossils at the tops of mountains, especially in our country, because most of the United States was a shallow inland sea for a very, very, very long time until the plates collided in the right way. And when it lifted those seas, the fossils or the dead organisms, as they fossilized, were carried up in elevation with them. Mountain range is just a group of mountains that are approximately the same age, the same shape, have the same rock content. So that would be, and I'm not sure which one I pulled in here. You guys pulled a picture. I liked it. It's pretty. We got the Rocky Mountain Range towards the west of us. We have the Appalachian Mountains towards the east of us. We have the Cascades that are more northwest of us. They formed at the same time because they came from the same plates that were colliding, that were converging. You don't need to know the chemical content. You don't need to know the ages of the mountain ranges. Some of you may have never been to the mountains before. You've only been in this area. There's also the Smoky Mountains in the east. That's what? Tennessee?
So technically, the very top of the mountain is the oldest part of the mountain.
Normally, obviously erosion occurs, okay, but in general, the highest part of the mountain range should have been there the earliest. So it would be the oldest part of a mountain range. Unless something weird happens. But yes, I mean, hypothetically, as long as nothing catastrophic has occurred, like a major earthquake that made, let's say, because on this picture, this looks like the top of the mountain, right? Very, very tip top, the apex of this range. But let's say there was a cataclysmic earthquake that occurred. And this one was a lot higher, but a big part of it fell off. But we don't know that unless we go back in time. But as long as something crazy like that happens, yes, the apex of your mountain range, like Mount Everest in the Himalayas, the very top of Mount Everest should be the oldest part of that mountain range. Plateaus. I should have put Devil's Tooth in here, but I didn't do it. Plateaus look like something came along, like a laser, and just shaved off the top, nice and flat. Aliens. You've ever seen Close Encounters of the Third Kind? The alien movie from like the 70s? Okay, so that thing that he builds with the mashed potatoes, that devil formation. You know what? Let me double check it because I'm sure it has like an official name. But is it called Witch Mountain? Let me double check. I don't want to. Whoa! Ooh, the pollen count's crazy. My phone is going nuts. Stop it, phone. There we go. At least the mountain cedar's not as bad now. Y'all, I was hurting the other day. Okay, so iconic plateaus. I think it's in Utah. If I put it up here, a lot of you would recognize it. Images. It's like in the middle of nowhere. There's nothing around it. Okay, let's try something else. So you have, and some plateaus, like the Colorado Plateau, is huge. It's multiple states large. It's a elevated area that in general, the very top of it is rather flat. Let's see. Land. I hate this phone. Y'all, I don't like iPhones. I'm not used to it. Landform. Put in Witch Mountain and it brought up a movie. I'm gonna have to look it up on my computer instead of my phone. A landform region. There are multiple ones in the United States. The Colorado Plateau that I was talking about, Devil's Tower. So I thought it was Devil's something. What is Devil's Tooth? Is it Devil's Tower? I'll have to double check it. This light blue part, yes, there's a little bit of features on the top, but this is a gigantic plateau. We are in a plain, well, let's see. We're give or take right here. So we're on the border of an interior plain and the Atlantic plain. So yeah, we have a little bit of hills and valleys here, but in general, this area is still considered a plain. It is a larger region, not just an isolated one, a larger region where the features are similar across that. I'll double check it. But it's, I'm looking for, okay, it is Devil's Tower. That is what it's called. It was Devil's something. But like I said, if I put it up here on the screen, some of you go, oh, I've seen a picture of that before. Very, very, very high. It looks like something came along with massive claws and raked all the way down the side of it. And it's completely flat at the very, very top. And it was in that movie, Close Encounters of the Third Kind, which is a much older movie. I mean, I think it came out before I was born. Like, it's been around for a long time. You guys should know what a map is. A map is a flat representation of an area. There are different types of maps. Some have way more distortion than others, depending on what of the three major types of maps there are. There's three different types of map projections. You should also know what a globe is. A globe is a spherical map. Now, the best way to be able to look at a map of our planet is to do so with the globe, because our planet is spherical and the globes don't distort. The maps distort. Some maps have way more distortion than others. Now, they always have the least amount of distortion at the equator, and they have the most amount of distortion towards the poles. They are drawn to scale. Like I said, though, maps have distortion. If you take a look at the classic flat map, Greenland looks huge. Greenland is not huge. It's just because Greenland is towards the North Pole, and as they flatten the map out, there's cracks in the map because it wants to be spherical, and they just fill in the cracks with land. I don't think I've got one on here, but I need to cheat and look. No. But you should know, you should know what a map is by now. You may not know that there's different types of maps, and you should know what a globe is. You have to know a scale with a map, especially if you are hiking in the backwoods, because your cell phones don't work in the middle of nowhere. Now, you can get a satellite phone, but those are expensive. But a regular cell phone, you're not going to get signal in the middle of nowhere. So you may have to resort to an actual map. If you don't know how to read the map and you don't know how to use a compass, you will get lost. Most people do not know how to read a compass at all. But on a map, somewhere, there is a scale. It's like a little legend. And it tells you how much distance, if you measure it with a ruler, what does it represent? There's different kinds of symbols that mean different specific things. And then somewhere on there should be a key or a legend to let you know which symbol means what particular landform, or does it mean a building? Does it mean a railroad? Does it mean a stream? What does that particular map use? And most of them are fairly universal. I will show you a topographic map at the end. Actually, I'm going to show you a couple of them, I think. It's hard to see on here. Our new copier copies everything extremely dark, and I don't know how to fix it. At least not from my computer. So we should know what the equator is. The equator goes around the middle of the Earth. The equator is at 0 degrees latitude. You will eventually learn more about latitude. Actually, I think this is the one that does latitude and longitude. Yeah, it does. But the equator splits our planet into the northern hemisphere, which is north of the equator, and the southern hemisphere, which is south of the equator. There is another line that splits our planet in half, and that is called the prime meridian. The prime meridian is at 0 degrees longitude. Okay, it actually goes through the very western part of Europe, like where Portugal is, and then goes down through the very, very western part of Africa. So the Ivory Coast is over there, and I don't know all my countries. Like I've said before, geography is not my thing. But the prime meridian is actually the boundary between the eastern and the western hemisphere. Anything to the right of it is considered the eastern hemisphere, and anything to the left of it is considered the western hemisphere. I have an exchange, or foreign exchange student from Spain, and he asked me yesterday, because the prime meridian goes basically through Spain, because does that mean that part of Europe is eastern and the other part is western? And I was like, technically, yes, but I'm pretty sure that those little bits that are truncated to the left of the prime meridian are still considered eastern with the rest of their country, or the rest of their group of countries. I think they are, but technically the prime meridian is the boundary between the two. So those are your two major lines. So just to show you what I was talking about, technically this is the Western Hemisphere, this is the Eastern Hemisphere, and Spain is like right there. So I'm not sure how that works. The equator, we've got the Northern Hemisphere, and we've got the Southern Hemisphere. Now I do know with the Northern and the Southern Hemisphere, for us, hurricanes, they spin counterclockwise because low pressures, but in the Southern Hemisphere, they would spin the other direction. Same thing with flushing the toilet. If you ever go and visit like Brazil and you flush the toilet and watch the water, it's going to spin it in the opposite direction than it does here. It just has to do with where it is in relationship to the center of the earth. I know, it's strange.
Spin the water the opposite way.
When you don't pay attention, okay, but when you flush the toilet, if you look at the toilet, the water spins a certain way. It is opposite in the Southern Hemisphere. Just like here, it's winter, there it's summer. It is. It's opposite on the Southern Hemisphere. Now, East and Western, no, but Northern, Southern, yes. Latitude and longitude, they're measured in degrees and minutes. I'm not getting into that. I may get into that later, but I'm not doing it right now. But latitude, the way I learned this, latitude is like climbing the rungs of a ladder. They go this way. They go up and down. They are in relationship to the equator. So they're either a certain amount of degrees and minutes north, like we are. Where I moved from, we were at just over 30 degrees north. I don't know where we are here. I'd have to double check it. I didn't install that app on my phone yet. But if you go below the equator, then you're so many degrees south. Longitude are the long lines that go up and down, either to the left, which is west of the prime meridian, so many degrees and minutes and seconds, or if you are east, to the right of the prime meridian, so many degrees and minutes and seconds. A degree is the larger, the only smaller would be a minute, and then would be a second. That's how they measure coordinates, which y'all don't do anymore. So once again, latitude is in relationship to the equator, north or south. Longitude is in relationship to the prime meridian, east or west. This is just to show you, like I said, latitude is literally like you're trying to climb a ladder. Longitude are long lines up and down. Technically, these are long lines east and west, but think of them as climbing the rings or the rungs on a ladder, and that is going north or south. Now we're getting into maps. There are three major types of map projections. And you're going to have all different kinds of stuff on your maps. They're going to look like they have grids on them. Those grids represent latitude and longitude. The first one that we're going to talk about is a Mercator projection. This is the most distorted map, completely flattened out. They fill in the gaps with land. So at the equator, there's the least amount of distortion. But towards the poles, like Greenland in the northern hemisphere, looks ginormous. These are the classic maps. These are the first types of maps that were done for forever and ever and ever ago. But those cartographers did all the mapping by hand. They used geometry. They didn't have satellites. They didn't have GPS. They didn't have any of that stuff. They literally went out into the wild and using the sun and geometry and shadows, they calculated this is how much distance went from point A to point B. We don't really do it that way anymore because we have technology. So towards the equator is going to be the most representative of what it's supposed to look like. The further north or south you go from the equator, the more distorted that map actually becomes. These are not good to use if you're out backpacking in the middle of nowhere. Once again, that is a Mercator type of map. Projection just means a map. We should finish within the next 7 minutes, I would think. So just to show you, this is a Mercator projection map. Y'all, this looks like Greenland is bigger than the United States. No. And since the equator is right here, the things that are along the equator are going to be the most representative of it. And then the things that are further away are not. But yeah, y'all, Greenland is it's not as big as South America, because in here they look, in fact, Greenland looks bigger than South America on this map. Okay, the next one, equal area projection maps. The image that I have for it, instead of it being square flattened out, it's like a globe that's been flattened out. So it's sort of curved on the edges. It looks like a really oblong map. Still has distortion towards the poles, but it's nowhere near as bad as a Mercator map. Mercators are the worst ones to use if you're actually trying to use a map to navigate. And honestly, nowadays, like, all you have to do is put it in your phone and it tells you everything you need to know. But like I said, if you're going into the middle of nowhere, these things don't work. You would have to have a satellite phone, but even then, that is only for communication purposes. It's like a glorified walkie-talkie. Although the technology may have changed since the last time I looked at those. So it's similar to a Mercator, but it's not square, I guess rectangle. It's like a huge smushed out oval. To show you, this is what an equal area looks like. Okay, so now you can see Greenland, which is up here, is not larger than South America. So this is better, but it's still not the best one if you're actually trying to use a paper map to do something. This is the type that is the most commonly used. This is a conic projection. There is still a tiny bit of distortion, but this is the absolute best map if you're using a map in order to use to be able to do some type of navigation. So basically they took the globe, they made a slit down it, and they opened it up. So longitude, up and down are straight, latitude is curved. Now with technology, there are other types of maps. These are the paper maps that we've used throughout history. The type that I've used when I was doing astronomy, it took me a while to get used to how to use it because everything is curved. You have to know your latitude and your longitude to be able to use those specific types of maps. And everything is curved on those maps. Ooh, it kicked on. It's going to get hot in here in a second. Okay, so Mercator, most distorted. That is the original type of map from forever ago. When, Columbus sailed the ocean blue and whatever year it was, 1462, I think is how that line goes. And then we graduated to the equal area projection. But as far as paper maps are concerned, a conic is going to be the best. Now let's get into some technology. Oh, no, before that. So the people that used to hand draw maps, they are called cartographers. Cartography is the art of creating a map. That is what that word means. They would use surveying equipment, which you may have seen surveyors before out, that you see these things that look like they're on a tripod. They're almost always like orange in color. It's like almost like a telescope that they're using during the day. those people make a lot of money. Those are called surveyors. And they're taking measurements of the boundaries of properties, or maybe you're selling off a part of land, and they put rods in the ground, and then they mark all this stuff off. That's called surveying. And then the original people had to actually go back and use geometry and shadows and timing in order to be able to do this. Modern equipment doesn't have to do that because everything's programmed nowadays. We use things called GPS. Once again, we didn't always have that technology back in the day. How much do we have? 1, 2, 3. 3 and then a picture. We use GPS all the time. You have GPS on your phones, you have GPS in your cars, GPS on everything nowadays. You get in an accident, a modern car, and you push that OnStar system button, they know exactly where you are. You don't even have to tell them, as long as your stuff is activated. Or whatever I don't even know if OnStar is the thing anymore. It's like a button. There's an emergency button on the top of modern vehicles. If you're in an accident, if you push it, it goes, it's like a 911 distress symbol or signal. Is it still OnStar? I know I've got one in my truck, but I don't never use it. Gosh, I hope I don't ever have to use it. All right, so a little bit about satellite imaging. If you've ever used Google Earth, the satellite records information as a pixel. Okay, so it takes whatever image it's looking at and it uses dots. 1s and 0s represent dots, which we call a pixel, and then the arrangement of said pixels creates an image. It has to do with how large the object is, the color, the brightness of the object. I mean, I'm sure you guys know what pixels are by now. We live in the digital age. But that's how the Google Earth is essentially put together. And there are different types of satellites that map. So some map the bottom of the ocean, and you don't necessarily get color of what the color is of the stuff under the water. The color represents different elevations. Almost there. All right, so nowadays cartographers use GPS. We don't normally use the old school methods anymore. I'm not saying that people don't ever use them like at all, but we rely on our electronics nowadays. We rely on our satellites. And they feed us the information of latitude and longitude in minutes, degrees, minutes, and seconds. Now, if we have an EMP or our magnetic field flips or something like that, we're going to have a major issue with our satellites. They won't work anymore. I heard the other day that we're about to have our first negative leap second. That time is going by at a slightly faster rate than it used to. And instead of adding a leap second, which is what they normally do to fix the atomic clock, they're getting ready to remove the leap second, which the satellites have not been programmed to deal with yet. And they don't know how that's going to affect the timing of the satellites in space.
Wait, so basically, how does that work?
I was trying to follow along with it when they were talking about it the other day, and I was like, how did the Earth speed up? Apparently, our rotation of our Earth has changed.
So that changes the time?
Yes.
What?
I had a hard time following along with some of this. I mean, I did at the beginning, and then they started trying to go into explaining exactly why it was happening, and I was like, I don't know if it was earthquake related or what, but apparently the rotation, not around the sun, but the day, it's changed, it's sped up.
So back then, it was going slower?
Apparently,
I'm saying,
I don't know. I'm gonna have to go into it and try to figure out why. I mean, if we have a large enough earthquake, yeah, it can affect the planet. It can mess stuff up. I mean, technically, if you took all biomass that had the ability to move and you put them in one spot and everything jumped at the same time, at the point that they leave the Earth, as they go up, the Earth must go down, and you actually push it out of orbit. Okay, but we're not going to float forever. So when we all come back down, which would create a ginormous earthquake, and all of our eardrums would rupture. But when you come down and as you come down, equal and opposite, so that the Earth would be snapped back into orbit. I'm not making it up. I'm not making it up. Newton's law says every action is an equal and opposite reaction. So if you jump up, you're technically pushing the Earth down. Yeah, I know. I have to look into it to see what they say happened. So I'm assuming it's earthquake related, but they didn't go into that. So the topographics show all the surface features, show the elevations, and we use what are called contour lines, these circular looking lines, in order to represent different elevations, relief, and slope. So what a contour line is, where that line touches, whatever elevation that line represents, that line is going to be the same elevation on all points. And we have specific intervals. It's normally, sometimes it's 4 lines, but it's normally every 5 lines. You see a darker contour line, and that's to help, so you're not having to count each individual line. Maybe every 5 is worth 100 feet, or every 5 is worth 200 feet. So it makes it easier to count elevation with these intervals. And they have to be, each line has to mean the same distance in between, or this doesn't work. Okay, don't worry about the bottom line. Okay, I did change it from tomorrow. We are going to learn how to read topographic maps, and I wish I had a bunch of foam paper so we could build it, but I don't. So I know what to order with my next round of budget money, because that stuff is expensive. And you need a lot of pieces of foam paper to make a topographic map the right way. ELEV stands for elevation. It is abbreviated. I'm going to show you a topographic and we're done. I'm going to go back and double check my attendance real quick to see if anybody was in there. This is what a topographic map looks like. This is Yosemite, right? Yes, this is Yosemite. So we see a river going through here. Now I can't read the numbers on there. I have to read the numbers on the thing. It's blurred too much. I can't read them. But this dotted line, this is a trail. We've got streams. These are roads. This looks like this is some type of like a camping area right here. We've got a building here. I can't tell what the actual, and I can't read any of the elevations. The stuff is too small. But this is what they look like. This one's a little blurry. I need to go back and see if wherever I got this image from, if I can get a clearer version of it. So let me go back to the right slide. Let me freeze it. Let me check online real quick. Attendance. So if you did not do the one from Wednesday, it's closing at midnight. Who else? Okay, now I see Natalie. I got you. And I see Sarah. I got you. So who am I missing? Caitlin? Is Caitlin on? Let me start this.